Hello everybody, I welcome all of you to this lecture. Okay, so we have started this oscilloscope unit and we have covered important things inside that. Okay, so we have seen this cathode ray tube in deep, which is very important. Then we have seen vertical deflection system. Okay, now in this lecture we will complete this delay line, this horizontal deflection system, inside which we have to see the trigger circuit, time base and the power supply as well. Okay, so these things we have to complete now. So it will complete the basic study of the CRO, and then we will see different types of modes and different types of CROs. Okay, so that will be very easy for you or for we to understand. Okay, so let's have a look on the points that we have covered till now. We have seen this cathode ray tube. Okay, so and its working we have seen. So inside that we have seen what do you mean by electron gun. Then we have seen what do you mean by this cathode, what is the use of that, anodes and vertical and horizontal deflection plates. Okay, so the different characteristics of this, we can say this phosphorus screen, which material is used and why it is used, that also we have seen. Okay, so we have seen this cathode ray tube. So after that we have seen the CRO front view. Okay, and I think I have shared one animated video with you which gives you clear idea about the working of this cathode ray tube and that electron beam, the deflection of that electron beam in horizontal and vertical direction. Okay, so this is the front view, and don't worry about this, we will see different panels and different control buttons on this front view of the CRO. Okay, after that we have seen vertical deflection system. Then we have seen how to apply the voltage and what will be the orientation or what will be the position of this electron beam or dot. So we have seen different types of voltages and different types of voltages which are applied to the that horizontal or vertical plates. Okay, so that also we have seen. Now in this lecture we have to start with the delay line. Okay, now the delay line is again very important. So why the delay line is required, that we have to study first, or we have to understand first. Okay, so all of the electronic circuits which we are using in the oscilloscope, they will take a certain time for their operation. Okay, that you have to understand, because if you see the oscilloscope, it is having number of characteristics and circuits, and if you see these circuits are constructed with the help of different types of components, and components having different components are having different delays. So all the electronic circuits that which are used in the oscilloscope takes a certain time for their operation or required operation, we can say. Okay, so if you see this electronic circuit includes attenuators, different types of amplifiers, then wave shapers. Okay, I think you have studied that wave shapers in analog and analog electronics design circuit subject. Okay, so I think you have studied in that. So whenever a signal is transmitted through this circuits, a certain time delay occurs. Okay, and if you see in deep characteristics of different components, okay, so you will understand the delay will be there. Okay, and due to that delay, if you add the each component's delay, then that will be a total circuits delay. Okay, so it may be in nanosecond, millisecond, okay, or in second, but that is a delay. There is a delay. Okay, but that is no much delay. Okay, so I think it will be in nanosecond or microsecond. Okay, so it will not be in seconds in terms of this CRO. Okay, and that you have to understand. Okay, but in different types of circuits it may be more than a second as well, based upon the components that we have used and based upon the working principle of that particular circuit. Okay, so if you see this figure, which is shown in slide, so some part of the output of a vertical amplifier, if you see this is the vertical amplifier, is applied to the trigger circuit. Okay, if you see, it is applied to delay line, but some part is applied to the trigger as well. Okay, So this trigger circuit provides a trigger pulse to the time based generator. Okay, so if you see this sweep generator, it is also called as a time based generator. Okay, so this trigger, the working of this trigger pickup is it is generally providing the trigger pulse to the time based generator. Okay, so why this trigger is required, that is why this trigger is required, that is very important to understand. Okay, so that we will see afterwards. So the output of this time based generator is applied to the horizontal amplifier, means this time based generator or sweep generator's output is applied to the horizontal amplifier. Okay, now this causes a considerable time delay for a signal to reach the horizontal deflection plates. Okay, so if you see here this vertical amplifier, suppose the delay line is not there, then we can say that suppose in first case, suppose the delay line is not there, then the vertical amplifier is directly connected to this plates. Okay, but if you see here the some part is applied to the trigger circuit as well, and it is connected to the sweep generator, and after it is connected to horizontal amplifier. Okay, now if you see in this path there are no any circuits if we neglect this delay line, or if we do not consider this for first case. And if you see this path, it is having some 3 circuits. Okay, so for time being we have to see this circuit, because actual circuit will be complex than this, but for understanding we have to consider this circuit as only. Okay, so if you see here 3 circuits are there. Okay, and due to this the delay will be there, that you have to understand. This causes the considerable time delay for a signal to reach the horizontal deflection plates, that is very important, and this time delay is more as compared to the signal reaching the vertical deflection plates, as we discussed earlier. Okay, now the time delay which takes place in the horizontal deflection system is generally about 80 nanosecond. Okay, so listen carefully, it is up to 80 nanosecond. So what we have to do is that a time delay of 80 nanosecond or more should be added in a vertical deflection system, so that they should be applied at the same time. Okay, or for the synchronizing purpose. So what do you mean by synchronization? Synchronization means what? Whenever the vertical amplifier or vertical signal is given to the vertical deflection plates, at the same time horizontal signal or horizontal we can say amplifier's output should be connected to the horizontal plates as well. Okay, so that is very important. So that is called as a synchronization. So the delay line is used to delay the signal for some time in the vertical section. Okay, generally a time delay of we can say the 200 nanosecond is provided to observe the leading edge of the waveforms. Okay, so if you see this diagram over here, okay, so if you see the general time plus 80 nanosecond is required. Okay, so suppose at t is equal to 0, without any delay line, at t is equal to we can say 0, suppose this vertical amplifier is connected to the or connecting the signal to the vertical deflection points, then what happens over here is that this horizontal signal is applied to the horizontal plates at t plus 80 nanosecond, means it is delayed by 80 nanosecond. So one thing keep in mind that we are not discussed about this delay line yet, we are just discussing directly. Okay, so why it is happening? So again we have discussed earlier, because vertical amplifier is directly connected to over here, but for synchronization purpose we require some trigger and sweep generator or time based generator, because synchronization is very important, and synchronization is nothing but connecting the this vertical and horizontal signals at a time. Okay, so that's why this for this synchronizing purpose we have to use this sweep generator. Okay, but due to this circuitry this is somewhat having a delay, so that's why we have to add a delay line. Okay, but generally we have discussed that 80 nanosecond is delay, but by considering all other delays and for better operation, generally 200 nanoseconds delay line is applied. Okay, so that is very important. So this time delay or the time delay of the 29 nanosecond is added here, and at the horizontal deflection plate the time delay is about 80 nanosecond. Thus the horizontal sweep starts prior to the vertical sweep, because what we have done is that suppose it is having a 80 nanosecond delay, and due to this delay line, now this vertical plates are receiving the signal at t plus 200 nanosecond. Now this vertical signal is delayed, we can say, or delayed. So due to this, what happens, the horizontal sweep starts prior to the vertical sweep. And what do you mean by horizontal sweep? That we have to see afterward, don't worry about that. Okay, so the leading edge of the waveform can be observed. Okay, So that we will discuss afterwards, why it is happening, or how the signal is displayed, and why the horizontal sweep should start prior to the vertical sweep. Okay, so this is all about the basics of a delay line. But if you see this diagram, this is the only circuit which we are talking about, and we have to explore more about this. So that's why we have to see the delay line, how the delay is actually obtained. Okay, so there are two types of delay lines which are used in the CRO. So one is called as a lumped parameter delay line, and another is called as a distributed parameter delay line. Okay, so these are the types of delay lines as we have discussed: the lumped parameter delay line and distributed parameter delay line. Now let us discuss about the first type, that is a lumped parameter delay line. Okay, now if you see here in this diagram or circuit, we can say you are observing some inductors and capacitors and one resistor which is having the characteristic impedance. Okay, so this is basic simple circuitry of a lumped parameter delay line or conventional parameter delay line, we can say. Okay, so if you see here, it consists of a LC network. Okay, so inductor and capacitor. Okay, so we will not talk about the actual values about this. We will just talk about the basics of this. Okay, again the delays of course depends upon what the values of L and C. Okay, but generally if you want to generate the delay from 3 to 6 nanosecond, then we can use this lumped parameter delay line. Okay, so it is also called as a T section because the combination of these two inductors and one capacitor looks like the T or character T. Okay, so that's why it is called as a, we can say, T section or T lumped parameter delay line. Okay, now here it is written over here that each section is capable of delaying the signal by 3 to 6 nanosecond. Okay, now I think you may have one question like this, that we require some 200 nanosecond delay, and this is giving you a 3 to 6 nanosecond delay. Okay, yes, it is, of course it is giving you a 3 to 6 nanosecond delay, but what we can do is that we can add the number of T sections so that it can be delayed. Okay, so if you, this is the single we can say T section, so it is giving you this 6 nanosecond delay, and after as per your use or as per your design, you have to increase this T sections in your circuit. Okay, so here the T section is terminated into its characteristics impedance Z0. I think you have studied the characteristic. What do you mean by characteristics impedance in circuit and network subject? Okay, so this is required to terminate. Okay, so the T section is terminated into its characteristic impedance Z0. Okay, so it acts as a low pass filter. Okay, I think you have studied the low pass filter and high pass filter as well, or you will study that. I will not go deep into that, just we will see the basics. Okay, the frequency up to which the low pass filter passes the signal is called as a cutoff frequency, and it is denoted by FC. So if you see this above LC network, the cutoff frequency of this LC network is given by FC is equal to 1 upon pi under root LC. Okay, so here it is shown that the frequency up to which the low pass filter passes the signal is called as a cutoff frequency. Okay, so beyond this frequency it will not pass, it will block. So that's why this is called as a low pass frequency. So if the frequency is less than the cutoff frequency, then this frequency is passed to the output, and if the frequency is above that, then it will not pass. So we have to take care while designing this lambda parameter delay line about the cutoff frequency, because suppose you are designing for some frequency which is having a higher values, and then this will not work. Okay, so that's why you have to take care about that. Okay, so if the frequency is less than the cutoff frequency, then this frequency is passed to the output, and the important thing is that it will be delayed by time delay TD, and that depends upon this FC, and that TD is given by 1 upon pi FC. So what do you mean by FC? FC is, if you put the value of FC over here, so TD will be, we can say, nothing but your under root LC. Okay, so that is again very important. So this is all about the lumped parameter delay line. So next is a distributed parameter delay line. So it is basically transmission line constructed with a wound helical coil, okay, and extruded insulation between it. Okay. So if you see, this is the outer conductor, then this is the insulation, this is the inner core, and this is the most important part inside this, that is the helical wound inner conductor. Okay, so it is a specially manufactured coaxial cable, looks like a coaxial cable, and it has a high value of inductance per unit length. Okay, so if you see, this is the construction of a distributed parameter delay line. Okay, so the inductance of this delay line can be increased. So if you want to increase the inductance, what you have to do is that the inductance of the delay line can be increased by winding the helical inner conductor on a ferromagnetic core. Okay, so this is inner core. If you replace this with the ferromagnetic core, then inductance will increase, which increases the time delay. Okay, so when you use the ferromagnetic core, it will increase the time delay. Okay, so that is again very important. Okay, so this is some basics about the distributed parameter delay line. Okay, so we have seen two types of delays, lumped parameter and distributed parameter delay line. Okay, now the next part is again very simple, and we have to talk about this, that is a horizontal deflection system. So right now we have discussed about CRT and vertical deflection system. Now we have to discuss about the horizontal deflection system. So inside that we have to see trigger circuit, then time based generator, okay, and the horizontal amplifier. So the circuit for this is again same. This is the trigger generator, this is the sweep generator or time based generator, and this is the horizontal amplifier. Okay, so let's discuss about this. So time based generator, why the time based generator is required, that we have to see. The time based generator is used to generate a sawtooth voltage which will deflect the beam in a horizontal direction. Okay, so if you see, the CRT spot is deflected at a constant time dependent rate, or we can say that constant time dependent rate that we are getting, that is because of this sweep voltage. Okay, so that we will see afterwards, don't worry about that. Okay, and I think you know that this time axis is represented as x-axis on the screen, and that time divisions we are calculating while calculating the frequency, that also we have to see afterwards. But see, one important thing is that this time based generator is generating the sawtooth voltage, and what is the use of that we will see in upcoming slides. Okay, so this is all about the time based generator. Now what do you mean by trigger circuit? Again, I think I have discussed about this. So it is circuit which ensures that the horizontal sweep begins at the same point, the vertical input signal. Okay, so something synchronization that is done by this trigger circuit, we can say. So without the trigger circuit, there will not be any synchronization between that sweep signal and the signal which is to be observed on the vertical deflection plate. That you have to keep in mind. Okay, so if you remove this trigger circuit, the synchronization will not be there, and on screen you may get a false readings or false waves, that you have to keep in mind. So that's why trigger circuit makes the synchronization in between horizontal and vertical systems. Okay, so that's why we have to use trigger circuit. Without trigger circuit, you will not get accurate waveforms on the screen. Okay, and the last but not the least is the horizontal amplifier. Again, it is similar to the vertical amplifier, which will increase the amplitude of the signal generated in the sweep generator or the sawtooth voltage to the level which is required by the horizontal deflection plates of the CRT. Generally, if you see the vertical plates or horizontal plates, these horizontal and vertical plates require some range or power of a voltage, and that is amplified by that vertical or horizontal amplifier itself. Okay, based upon that requirement, that is only use of that vertical and horizontal amplifiers. Okay, so this is all about the horizontal deflection systems. Okay, now we have to study the last point from this main blocks of the CRO, that is a power supply. Okay, and you cannot neglect that. Okay, so again, it is very simple that a power supply is used to supply the power to the different circuitries and different parts inside the CRT, that is cathode ray tube or a CRO. It provides the voltage required for the CRT to generate and accelerate the electron beam, and the voltage required for the other circuitry. Okay, see, you have to design the power supply in such a way that it should produce the voltage requirement of the CRT to produce that electron beam. That is the one major part inside the CRO. And another important thing is that there are some simple circuitries, and for that circuitries you may require the other smaller supply voltage or smaller current requirement. Okay, so that is again very, we can say, complex design. Okay, but this power supply is very important and you must understand this. Okay, so now we will talk about the two power supplies which are mainly used as a negative high voltage and positive low voltage. Okay, so see, this negative high voltage is given by minus HV and the positive low voltage is given by positive LV. Okay, so here if you see the range, just keep this range in your minds. I think while discussing that electron gun, I think I have explained about that, how to apply the voltage and what should be the amplitude of the voltage for that pre-accelerating anodes and the cathodes and all other things. Okay, so you have to see that previous lecture, my lecture, in which I have talked about the voltage requirements. But generally, if you see the high voltage, that is negative high voltage, that is in the range minus 1000 volt to minus 1500 volt. Okay, that's why it is called as a high voltage and that is a negative. And if you see the low voltage, it is no doubt it is positive and it is from 300 volt to 400 volt. Okay, so these are the major power supplies. But one another important thing is that some simple circuitry may be there, and this circuitry requires different types of voltage, low voltage. Okay, so that also designed by designer while designing the power supply. Okay, so this is all about the power supply. Now let's discuss this last point from this part only. Okay, the unit is not yet completed, but this part is how signal is displayed, that you have to understand. Okay, now previously we have seen that the sawtooth waveform is applied to the horizontal deflection plates, but you must know how it is applied. Okay, so if you see here, these are the horizontal deflection plates and the Vx is applied. Okay, so if you see the sawtooth waveform, that is applied to the right plate of a horizontal deflection plate, and if you see the left horizontal deflection plate, it is connected to the ground. Okay, so that is very important to understand. Okay, again I am repeating, this right side or right plate is connected to the sweep voltage and or sawtooth voltage, we can say, and left plate is connected to the ground. Okay, now why it is done so, let's understand with the help of this diagram. So if you see, this sawtooth waveform is generated by the special unit inside the oscilloscope, which is called as a sweep generator or a time based generator. So this sweep generator or time based generator is same. Okay, now let us assume that the voltage applied between the vertical deflection plate is 0, that is no input signal is applied to the vertical plates, we can say. Okay, now what happens over here is that a sawtooth voltage Vx is applied between the horizontal deflection plates over here. Okay, so at instant A, look here, at instant A, the sawtooth voltage is 0. Okay, and the beam, the electron beam is on the extreme left of the screen. So if you see here, it is the extreme left that is shown over here. So at the extreme left, the beam will be there. Okay, now as the Vx increases, the sawtooth voltage will look like this. Okay, so this is a sawtooth voltage, to keep in mind. So the sawtooth voltage will look like this. Okay, now as the voltage Vx increases, the potential on the right plate starts increasing. Okay, because it is connected to 0, and this voltage will increase slowly, so it will look like this, and the Vx increases, the potential on the right plates. Okay, so as we go on increasing the potential, the electrostatic field is developed, and the field strength of the field strength also increases with respect to this Vx. Okay, and due to this increased field, okay, what happens over here is that this electron beam is pulled towards the right hand side of the screen. Okay, so as we go on increasing the voltage, what happens over here, the beam's spot or that dot will move towards the right, like this. Okay, so direction of the spot movement will be right based upon this Vx. Okay, and as the sawtooth voltage Vx increases linearly with the time, the field also increases, and the beam travels at a uniform speed from left to the right, that you have to keep in mind. Okay, but what happens over here is that as the sawtooth voltage reaches the peak point, okay, peak point, so this is your peak point, that is P. What happens, the beam will reach extreme right of the end of the screen, so it will be at the extreme end. If you see here, it will be at a extreme right end. So the time taken by Vx to rise from 0 to peak voltage corresponds to the time taken by the spot to move from the left to right. That is very easy to understand, and that is called as a trace time. Okay, so again I am repeating, the time taken by this Vx from this to this, okay, this to this will be equal to the spot, the time required to the spot to move from this point to this point, and that is called as a trace time. Okay, and then the voltage Vx, what happens here is that then the voltage Vx reduces suddenly from its peak to 0, and due to that what happens is that the electrostatic field also collapse, and beam is returned back to the extreme left of the screen, and that time, so if you see this slope, decreasing slope, that is called as a flyback or a retrace time. Okay, and the beam is blanked out during the retrace time, so that the retrace is not visible on the screen. Okay, so only trace is visible, and during retrace we can say the beam is blanked, so that's why you are not getting the retracing. So that's why the retrace is not visible, only trace is visible. Means what, only this part is visible, this moment is not visible. That is called as a retrace or a flyback time. Okay, so we will understand more about this while studying the different types of CROs. Okay, and I think for today's lecture this much is sufficient. Just see carefully what we have studied over here, that power supply and the horizontal deflection plates and all other things. Okay, so I think now it is clear. Now it's time to see different types of controls of a CRO. Okay, so that we will see in next lecture, which are different panel controls and all other things, and after that after studying the basic controls, we will move towards the dual trace oscilloscope, and we will study the different alternate and chop modes as well. Okay, so this is the basics about the working principle and the main circuitry and main parts of the CRO. Okay, and I think you understand this very well. Okay, now it will be very easy for me to teach you the next part. Okay, because after studying the basic parts or basic circuits inside the CRO, you must know how to use the CRO. That is very important thing. Okay, so that we will see in next lecture, and I think in last lecture as well I have given you some homework, and that also we will see in next lecture. We will talk about that because that is very important. Okay, so that this is all about the working principle of a CRO. Okay, so if you have any doubts, then you can ask me. Okay, so for today's lecture this much is sufficient. If you have any doubts, you can message me, no problem. Okay, so just study this CRO in deep because this is very important. As an electronics engineer, you must know different types of measuring equipments and all other things, and out of that the function generator and CRO, basically CRO, cathode ray oscilloscope, is very important. Okay, so just study that in deep, and if you have any doubts you can ask me, and we will meet in the next lecture. Okay, thank you very much. Thank you.